For a long time, physics has upheld a limited vision of reality. It portrayed the universe as a deterministic mechanism, or, when randomness seemed to appear, invoked the mysterious collapse of the quantum wave function. Yet, this presumed collapse has never been observed, only postulated. What has been observed with extraordinary precision is quantum behavior that shows no signs of discontinuity or singular events. Instead, what unfolds is simple. Everything that can happen does happen, but not in a single universe. The most rational, if profoundly challenging interpretation, proposes that we live in a multiverse. This is not a metaphysical speculation, but the inevitable conclusion of taking quantum mechanics seriously. From this standpoint, what we consider reality is merely a tiny portion of an immense and profoundly complex whole, a superposition of coexisting histories, all real, all unfolding simultaneously. In this view, every choice you make, every subatomic motion that transpires, bifurcates the universe into multiple versions. You, right now, sitting here reading these words, also exist in countless alternative variants, some only slightly different, others radically so. These versions do not dwell in speculation. They are real, coexistent, and all are described by the same theory that predicts the outcomes of every modern physics experiment with astonishing accuracy. The human mind, accustomed to a single, linear narrative, finds it difficult to accept this multiplicity. Yet physics does not bend to our intuition. Rather, our intuition must expand if we aspire to truly understand what is happening. This is the direct consequence of abandoning the artificial construct of collapse, allowing the wave function to evolve uninterrupted, just as every other natural law does, reveals a compelling and unsettling panorama. Reality is a tapestry woven from multiple versions of every event. This interpretation also offers a powerful framework for understanding randomness itself. What appears to us as chance or unpredictability is, in truth, a reflection of our limited access to the totality of the multiverse. Outcomes aren't determined by hidden variables, but by the branching of reality itself, where each possible result is actualized in a distinct universe. This concept is not new. Hugh Everett III first formulated it in the 1950s, though it was widely ignored for decades. Today, however, with a more mature understanding of quantum theory and the explanatory power it offers, Everett's proposal is recognized not as extravagant, but as inevitable. A paradigmatic example of this phenomenon is Schrödinger's famous thought experiment. A cat is placed in a sealed box with a quantum-triggered mechanism that may or may not release poison. Under traditional interpretation, the cat exists in a superposed state, both alive and dead, until someone opens the box and observes. From the multiverse perspective, however, there is no ambiguity and no collapse. Instead, two realities exist. One where the cat lives, another where it dies. Both realities endure, and the act of observation simply reveals which branch the observer occupies without eliminating the other. This is not a mere play with paradoxes. It is a profound statement about the structure of reality. It transforms our understanding of existence, identity, and truth. By embracing this interpretation, we shed outdated illusions about singular existence and realize that reality is richer than any single narrative can convey. Every moment branches, every possibility truly occurs, and though our conscious experience remains tied to one branch, the rest continues to unfold, hidden yet fundamentally real. Accepting that the universe is not unique marks a profound shift in how we perceive reality. Hugh Everett's many worlds interpretation is not some decorative flourish within quantum mechanics. It's one of its most consistent and natural conclusions. The idea of branching universes isn't a matter of philosophical taste. It's what emerges when quantum theory is applied without artificial constraints. Traditional quantum theory describes systems evolving smoothly and deterministically via Schrödinger's equation until a measurement is made. Then abruptly, the system is said to collapse into a single outcome. But this collapse has never been directly observed. What we observe is simply the result. The collapse itself is a theoretical convenience that disrupts the uniformity of physical laws. Everett's bold proposal was to eliminate this narrative device altogether. Let the quantum evolution proceed unbroken, always. Doing so leads to a dramatic yet unavoidable implication. Every possible outcome does occur, each in a separate version of the universe. Each time a quantum event allows for multiple outcomes, the universe doesn't select one, it branches. Each result manifests, not metaphorically, but as a concrete instance within a larger structure. These branches don't resemble familiar, visible pathways. They're abstract, independent strands described by the same equations and evolving side by side. But this process is not chaotic. While all possible outcomes occur, they do so in varying degrees. Imagine flipping a coin. Half the worlds register heads, half tails. Yet in a tiny number of universes, the coin might hover mid-air, dissolve, or behave unexpectedly. All of these outcomes are real, but not all are equally prevalent. The multiverse has structure, governed by probabilities, not randomness. In this context, possibility takes on a new meaning. It's no longer about what could have happened but didn't. It's about what did happen, just not here. Possibility becomes a category of existence. What we call chance is simply our limited perspective within a single branch, blind to the others. This perspective is not speculation. It's grounded in the very mathematics of quantum mechanics. The multiverse is not an imaginative flourish. It's an objective framework where parallel realities emerge naturally. This forces us to step down from the idea that the universe is crafted around us. We are not at its center. We are one version among many. What is real must expand to include all that exists within the scope of physical law. By embracing this framework, we allow our understanding of existence, identity, and truth to evolve. It requires leaving behind deeply held intuitions, but in return, it offers a coherent, richly structured picture of the cosmos. In this view, every decision, every measurement, every quantum fluctuation is a branching point. Our awareness may be bound to one path, but the others continue, just as real, just as significant. This branching is not speculative. It's testable, predictive, and increasingly essential to explaining quantum phenomena. Rejecting the many worlds view requires inserting arbitrary limitations into an otherwise seamless theory. By contrast, embracing it reveals the universe's true scale, one in which everything that can happen does happen somewhere. The popular idea that we live inside a simulation is, in most forms, a philosophical misunderstanding. Rather than confirming that notion, quantum computation offers a far deeper and more compelling insight into the structure of reality. The real question isn't whether we're inside a simulation, but how abstract structures like mathematics and computation can so perfectly align with the laws of physics. For a long time, computation was seen as a tool invented by humans. But the discovery of quantum computation showed that computing isn't just something we do. It is embedded in the universe itself. Physical systems, when built properly, can simulate other physical systems. This doesn't imply we're being simulated, but that our universe contains within it the potential for universal emulation. This shifts our focus. Instead of imagining a simulation running on some external device, we ask why our physical laws allow for machines that can simulate the very universe they inhabit. The answer lies in universality, the capacity for a physical system to replicate any other, not through superficial copying, but by following the same fundamental rules. Quantum computation unites physics and information in a way that reveals deep truths. The universe is not random in its structure. It is built in a way that supports the emergence of knowledge, models, and self-understanding. Quantum computers show us that phenomena like superposition and entanglement are not just curiosities, but essential tools for harnessing the nature of reality. These machines are not just faster versions of classical ones. They represent a fundamentally different kind of computation. They can solve certain problems so efficiently that even a classical computer the size of the universe would fall short. This power comes not from magic, but from physics itself, from the way quantum systems interact. More importantly, quantum computation proves that information is not passive. In quantum mechanics, information has causal power. It interferes, combines, and alters outcomes. It's not merely stored. It shapes what happens. Importantly, this realization reframes our understanding of mathematics. It's not merely a language we use to describe patterns. It's woven into the very fabric of the cosmos. The laws of physics themselves prescribe the computational capabilities of matter. In this light, what once seemed speculative becomes necessary. Computation is not incidental, but fundamental. That is why the ability to process information isn't just a feature of the universe, it is a consequence of its laws. What we learn from this is that our universe is not a simulation. It is something even more extraordinary. It is a system capable of generating the conditions for understanding itself. Knowledge is not imported from outside. It emerges from within, from configurations like brains or machines that embody truths about other parts of reality. In short, quantum computation doesn't trap us in illusion. It reveals the astonishing coherence between physical laws and the power of thought, of simulation, and of explanation. This isn't evidence that the universe is artificial. It's proof that it is intelligible. Understanding the universe is not about collecting disjointed facts. It's about weaving deep explanations that together reveal the structure of everything. 4 fundamental theories form the backbone of this unified vision: quantum physics, evolution, computation, and epistemology. Each on its own is powerful, but it is in their interplay that we uncover the most profound insights into reality. Quantum physics explains the behavior of matter and energy at the microscopic scale. It's the most precise and tested theory in history, not just about particles, but about how reality unfolds. Its most compelling interpretation, the multiverse, tells us that reality consists of multiple versions of every possible event. Probabilities don't reflect ignorance. They arise from a real structure of coexisting stories, each just as real as the next. Evolution in turn illuminates how knowledge arises in biological systems. Adaptation is not merely a biological process. It's a method of encoding useful information into matter. DNA doesn't just describe life. It embodies knowledge that has solved real problems in real environments over time. Evolution is thus not only a theory of biology, but a theory of how knowledge originates, survives, and improves through selection. Computation, when understood as part of physics, reveals a startling truth. Any physical process can, in principle, be computed. A universal computer is not just a tool. It's a reflection of the fact that the laws of nature are structured in a way that permits the creation of knowledge. This doesn't reduce the universe to a simulation. Rather, it shows that the universe is capable of creating internal models of itself, both in minds and machines. Finally, epistemology, the theory of knowledge, ties everything together. Knowledge isn't a static list of facts. It is made up of explanations, ideas that cannot easily be changed without losing their explanatory power. A good explanation isn't just something that predicts outcomes. It reveals what is actually present. The growth of knowledge is driven by bold conjectures and critical testing, a process that offers no guarantees, but endless potential. These four theories do not stand in isolation. They reinforce each other. Quantum physics makes possible the existence of brains and computers. Evolution explains how entities capable of understanding come into being. Computation allows us to simulate and experiment. Epistemology directs and refines that process. Alone, each theory is powerful. Together, they form a cohesive structure that describes reality at its deepest levels. This interconnectedness also redefines our role as observers. We are not merely passive recipients of knowledge, but active participants in its creation and refinement. The tools we use, scientific theories, computational models, evolutionary insights, are not separate from us. They are extensions of our minds, shaped by our need to make sense of the universe and our place within it. What's remarkable is that none of these theories impose rigid limits on what can be known. Instead, they show how knowledge can grow without bound. We don't inhabit a universe frozen in deterministic inevitability. We exist in a creative multiverse, where the right ideas can reshape what is possible. There is no script, no pre-written fate, just a vast landscape of opportunity, shaped and navigated by understanding. In the multiverse interpretation, time is not a simple linear procession as we typically perceive it. Rather than a sequence in which events arise and then vanish, time is an intricate and simultaneous dimension where multiple realities coexist and continually shape one another. As the universe evolves, it does not unfold as a single continuous stream, but rather as a vast web of timelines that begin in sync and then branch off into deeper, diverging paths. Each quantum event drives the formation of new parallel variants, not by creating something entirely new, but by unfolding what was already latent. This ongoing branching is what gives rise to the phenomenon we experience as the arrow of time. The past, by contrast, is a region where these variants remained nearly identical. The present marks a bloom of divergence. And yet, as these universes drift apart, they do not become entirely isolated. They remain linked through quantum interference, microscopic effects whereby parallel histories subtly affect one another, though such influence is nearly undetectable on a human scale. These interferences have been confirmed in laboratory experiments, reinforcing the notion that these parallel universes are not abstractions, but active participants in quantum dynamics. Such experimental validations are not just academic curiosities. They are windows into the fundamental workings of reality. Each interference pattern we observe provides direct evidence that what we perceive as singular events are actually the visible shadows of countless overlapping alternatives. These phenomena invite us to rethink causality, identity, and continuity, not as givens, but as emergent illusions. Our experience of time, then, is not embedded in a flowing stream, but rather in this underlying structure. The concept of a single self journeying through time is a useful but misleading illusion. In truth, there are multiple versions of oneself. The version from 10 years ago, the version now, the version in the future. Each exists fully and coherently in this timeless structure. We are not single beings progressing through a line. We are many interconnected individuals inhabiting different branches, each a partial manifestation of a larger self. This perspective aligns with ancient intuitions about identity and change, yet it pushes even further. Einstein's relativity already taught us that time is not uniform. No single, absolute present exists. Now, quantum mechanics adds a further twist. There is no single universe. Together, these insights reveal a view of reality in which both time and space emerge from the deeper structure of the multiverse. From this vantage point, time's passage neither erases the past nor privileges a singular future. Instead, it maps out a quantum geometry in which all stages of existence are equally real. Cause and effect appear as emergent patterns, but the totality exists simultaneously. Memory, anticipation, and the present moment are just different shapes that this structure takes, not standalone or superior realities. This conception of time has profound implications for rationality and ethics. If the self is better understood as a node within a network of possibilities, then personal identity itself is transformed. Responsibility and concern no longer apply solely to one timeline, but extend to a family of branching realities. Decisions matter not only here and now, but across this web of diverging universes. Rational thought must account for local impacts as well as consequences that unfold across these many branches. The intellectual challenge is vast: to accept the realness of multiplicity and simultaneity, to abandon the comforting notion of a singular time flow and embrace the immensity of the multiverse is an act of cognitive humility. It highlights the limits of our perception, the fragility of our intuitions, and the overwhelming consistency of the physical laws that govern everything. In this light, time is no longer a philosophical mystery. It becomes an emergent property of a richer quantum structure. The passage of time is but a path within an endless forest, and the true nature of reality is the forest itself, a rich, creative, eternal entanglement in which every instant blooms like a unique flower, as real as the one that will bloom tomorrow. Quantum computing is not merely an emerging technology, it is a window into the very fabric of reality. Traditionally, computation was viewed as the manipulation of symbols, algorithms, and numbers, a purely abstract pursuit. Yet quantum mechanics has redefined computation as a fundamentally physical phenomenon, governed by the laws of the universe itself. When Alan Turing first articulated his theory of computation, he approached it from the realm of mathematical logic. His now famous Turing machine was a conceptual tool, created to define what could be computed. What was unimaginable at the time was that this abstraction would one day become a matter of physics. A real computer is not a Platonic ideal, but a physical entity bound by the laws of nature. Therefore, what is computable is ultimately determined by the nature of those laws. Should those laws change, so too would the limits of computation. This is where quantum computing emerges. Unlike classical machines, which process bits, units of information that can only be 1 or 0, quantum computers operate with qubits. These qubits can exist in superpositions, embodying multiple states at once. This allows quantum machines to explore numerous computational pathways simultaneously. The real revolution, however, lies not just in this parallelism, but in how solutions are extracted. Through quantum interference, correct outcomes are reinforced. while incorrect ones cancel each other out. This is not guesswork. It is a form of constructive computation that defies classical logic. A quantum computer with merely a few thousand qubits could outperform all classical computers in the observable universe, executing more simultaneous operations than billions of machines running in parallel. Yet, this power is not universal. For most everyday tasks, classical computers remain more efficient. But for specialized problems, such as simulating complex molecules or factoring vast integers, quantum computing offers unprecedented capabilities. What matters most is not just speed, but what this capability reveals about our universe. The very fact that universal computers can be constructed within our universe indicates something extraordinary. Our physical laws are themselves computable. Not every conceivable universe would allow this. Most would be chaotic or incoherent, incapable of supporting structured systems like human brains or computational devices. Ours, remarkably, does. This fact is not incidental. It underpins the very possibility of knowledge, science, and life itself. Thus, reducing the universe to a mere computer is not only simplistic, it misses the point entirely. The universe is not a simulation running on some external machine. What is truly remarkable is that it contains within itself the potential to create universal computers. This is a property of the universe, not of something beyond it. It's not that we live in a computer, but that our universe is structured in such a way that computation, representation, and transformation of knowledge become possible. Perhaps most striking is how quantum computing challenges our deepest intuitions. For centuries, mathematicians and logicians developed theories of computation rooted in classical assumptions: pen and paper, finite steps, binary logic. They believed they were defining abstract boundaries, but in reality, their thinking was constrained by the physical world they inhabited. Paper, after all, is a quantum object. By relying on classical reasoning, they overlooked the true scope of what could be computed. Only when quantum physics entered the conversation could those assumptions be re-evaluated. Quantum computation is not merely a blueprint for building new types of machines. It is a physical theory of what kinds of transformations can occur within the universe. And because computation is fundamentally about representation and transformation, it becomes a theory of knowledge itself. Wherever there is computation, there is the possibility of encoding, modifying, and improving explanations. And where there are explanations, there is the potential for progress. In this sense, quantum computation is not simply a chapter in the history of technology. It is a pivotal concept in understanding the relationship between the universe and knowledge. The universe is not passively computed from without. It is actively computable from within. That makes it not a simulation, but something far richer. A place where knowledge itself is a causal force. Human progress does not depend on spotting patterns or merely accumulating data. It hinges on the creation of profound explanations about reality. An explanation is not just a compelling story. It is a proposal that endeavors to describe what exists, how it operates, and why. Yet explanations are not all equal. The most valuable ones are those that cannot easily be altered without destroying their explanatory power. Take, for example, the claim that a magic trick succeeds due to real magic. That explanation fails entirely. It can bend to fit any outcome, granting it no real explanatory weight. The same applies when we reduce complex phenomena to empty phrases like "something happened." By contrast, explanations grounded in the theory of evolution or relativity do more than clarify the unknown. They open up entirely new avenues for exploration. What separates the trivial from the transformative is not mere predictive capability, but the difficulty of varying that explanation. This principle transcends the traditional scientific method. Knowledge advances not simply when hypotheses are tested, but when ideas encounter reality, and only the most robust survivors endure. Many philosophical errors stem from neglecting this standard. Take extreme empiricism, the belief that only what is directly observed can be discussed. That stance is self-defeating. The assertion, only the observable is real, is itself not an observation, but a philosophical claim. If taken literally, it forbids discussion of atoms, black holes, even dinosaurs, because we have never seen them alive. Yet, we possess solid explanations that affirm their existence. Such philosophies do not correct error, they perpetuate it. By rejecting theories that are not directly observable, they constrain scientific imagination. Ironically, many such ideas began with the intention of protecting science, yet end up as its shroud. Thus, it becomes essential to distinguish between science and reason. Science is a concrete application of reason to phenomena in the physical world. Reason, however, encompasses a much broader domain. It is the capacity to generate good explanations in any field. It underpins not only science but philosophy, ethics, politics, aesthetics, indeed, any domain where ideas matter. Believing that only science can produce knowledge constitutes a modern form of reductionism, scientism. This notion asserts that every legitimate question must have a scientific answer. Yet such a stance inherently dismisses all forms of progress outside its current methods. History proves otherwise. Many fields now considered scientific, such as cosmology, began as branches of philosophy until they developed testable explanations. Science expands not by rejecting philosophy, but by assimilating philosophical questions once they become testable. The real criterion for progress, then, is not method, but the pursuit of good explanations. That principle allows us to discern whether we have encountered a fertile idea or a logical trap. It extends far beyond science. In moral, political, and aesthetic domains, we too can distinguish arguments that foster progress from those that merely reinforce prejudice. This approach also challenges the notion of eternal mysteries, things we are destined never to understand. Throughout history, phenomena once considered inexplicable, fire, planetary motion, the origin of life, became intelligible. There are no guarantees that all mysteries will be solved, but there is ample evidence that knowledge is intrinsically improvable, and that is enough. The universe is not compelled to be comprehensible, but it is, not by design, but because our cognitive capacities have evolved to discover deep truths. The existence of computers, languages, science, and culture demonstrates that knowledge is not an illusion. It is a genuine force that transforms the world. Thus, the limits of knowledge are not technical but philosophical. To cease seeking explanations is to stagnate. To assume we already know everything is to stop learning. But as long as there remains the will to inquire and the readiness to revise beliefs, progress is possible. The challenge is not to know everything, but to continue knowing more. Knowledge may not be boundless in content, but it is infinite in its potential for improvement. There is no final destination, only a horizon that expands with each step forward. This is precisely why education, if it is to be meaningful, must not merely transfer facts, but foster the habit of explanation. The goal is not rote learning, but cultivating minds that ask why and pursue better answers, even at the cost of discarding cherished beliefs. In a world shaped by good explanations, education is not about conformity. it is about continual revolution. Each generation has the chance to push the boundary of what is known, not through memorization, but through fearless inquiry grounded in reason and a shared commitment to intellectual honesty. Ultimately, authority does not reside in experts, tradition, or intuition. It resides in the best explanation available at any time, and that explanation can shift. Therefore, critical thinking is not merely a desirable skill, it is an absolute necessity. The future belongs to those who do not fear changing their minds, because where there is reason, there is always hope. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.